Now, we're going to take up one more problem. Problem number 53. It reads as a solid steel bar of 500 mm length and 70 mm in diameter is placed inside an aluminium tube having 75 mm inside diameter and 100 mm outside diameter. The aluminium cylinder is 0.15 mm longer than the steel bar. An axial load of 600 kN is applied to the bar and the cylinder through rigid cover plates as shown in the figure. So here you have a solid steel bar of 500 mm length and 70 and this diameter is 70 is placed inside an aluminium tube. So you have this hatched portion is the aluminium tube having inside diameter is 75. So this diameter is 75 and the outer diameter is 100 mm. The aluminium cylinder is 0.15 mm longer than the steel bar. So steel bar is longer than, so steel bar has 500 mm. So aluminium bar is 0.15 more than what the steel bar. An axial load of 600 kN is applied to the bar and the cylinder through the rigid cover plates. So this is the rigid cover plates. Find the stresses developed in steel bar. So what is the stress developed in steel bar and also aluminium tube? Assume Young's modulus is 210 kilonewton. Young's modulus of steel is 210 kilonewton per mm square and Young's modulus of aluminium is 70 kilonewton per mm square. Now, how to solve this problem? So we have the data which has been given where length of steel bar is 500, diameter of aluminium, that is the inside diameter of aluminium is 75 and the outside diameter of aluminium is 100. So diameter of steel bar is 70. So the load applied, which is the compressive one, which is 600 kilonewton, which is 6 into 10 to the power of 5 Newton. And Young's modulus will be equal to 210 kilonewton per mm square, which is nothing but 2.1 into 10 to the power of 5 Newton per mm square. And Young's modulus of aluminium is 70 kilonewton per meter square mm square, which is 0.7 into 10 to the power of 5 Newton per mm square. So first we are going to find out what is the area of steel bar. Area of steel bar is pi by 4 into 70 square, which will be equal to, on simplification, 3848.45 mm square. Similarly, area of aluminium tube, which is AAL, will be equal to pi by 4 into 100 square minus 75 square, which will be equal to, on simplification, 3436.117 mm square. So what is the load required to compress aluminium tube by 0.15 mm? So initially I need to calculate what is the load which is required to compress this 0.15 mm. So that this rigid plate will comes in contact with the aluminium also, with the steel also. Initially now the rigid plate is only in contact with the aluminium tube, whereas steel doesn't have that. So actually the load applied is 600 kilonewton. So that 600 kilonewton is applied only to the aluminium. It is not touching the steel bar. So what is the load required to compress this 0.15, which we need to calculate. So that is what we wanted to do here. So that is tube by 0.15. Therefore, delta will be equal to P into L by A into E. So P into LAL by AAL into EAL. So what is the delta, which is 0.15, will be equal to P into length of aluminium is 500 plus 0.15, which is 500.15 divided by area of aluminium, which is 3436.117 into Young's modulus of aluminium is 0.7 into 10 to the power of 5 or 70 into 10 to the power of 3. So on simplification, you will going to get it as P is 72,136.8 Newton, which will be equal to 72.137 kilonewton on simplification. So what is the remaining load? The remaining load will be equal to PR will be equal to 600 minus 72.137, which will be equal to 527.863 kilonewton. So this load will be shared by both the steel and the aluminium tube. Naturally, PRS and PRAL, remaining load of steel and remaining load of aluminium, will be equal to PR. PRS plus PRAL will be equal to 527.863 kilonewton. Also, delta LRS will be equal to delta LRL, which is PRS into LS by AS into ES is equal to PRA into LRA divided by AAL into EAL. So what is PRS that I need to find out? Into length of steel is 500 and area of steel is 3848.45 into Young's modulus of steel is 2.1 into 10 to the power of 3. 2.1 into 10 to the power of 5. So PRAL will be into 500 divided by 3436.117 into 0.7 into 10 to the power of 5. So on simplification, PRS will be equal to 3.36 into PRAL. So you substitute the value of PRS as 3.36 PRAL here, plus PRAL will be equal to 527.863. Therefore, on simplification, PRAL will be equal to 121.07 kilonewton. So what is remaining load of the steel? The remaining load of the steel will be equal to 527.863 minus 121.07, which will be equal to 406.793 kilonewton. Therefore, total load shared by the aluminium tube, which is PAL, will be equal to PRAL plus PAL. So that is 121.07 plus 72.137 will be equal to 193.207 kilonewton. So what is the load shared by the steel bar? The load shared by the steel bar, which is PS, will be equal to the remaining load, which is 406.793. Stress induced in the steel rod, which is sigma S, will be equal to PS by AS. PS is 406.793 into 10 to the power of 3 divided by AS is area of steel bar, which is 384.8.455. So on simplification, you will going to get it as 105.7 Newton per mm square. So what is the stress induced in the aluminium tube, which is sigma AL, will be equal to PAL by AAL. So what is PAL? PAL is nothing but 193.207 into 10 to the power of 3 divided by 3436.117 AAL. So on simplification, you will going to get it as 56.23 Newton per mm square. So this is how you will be able to calculate this, but you will be able to solve this particular problem. If you find this video will be useful to you, then please subscribe to my channel. Thank you.